Hello everyone, welcome back. Today we are going to discuss quantum mechanical model of atom. Having discussed Rutherford's model, Bohr's model, we find some demerits or disadvantages of these models. Some of the disadvantages of Rutherford's model were overcome by Bohr's model. Even after having so many important discussions, important derivations from Bohr's model, Bohr's model has got some very important demerits. Bohr's model basically was based on the particle nature of electrons. Considering the particle nature of electrons, we have derived a number of important derivations from Bohr's theory. So later on, it was found the electron also shows dual properties, that is wave nature as well as particle nature. Considering the wave nature of electrons, the well-defined trajectory called orbits as were defined in Bohr's model could no longer be ascertained, because when we define electrons to behave as if like a wave, the exact location or the position or the momentum of that particular wave at any instant cannot be exactly measured. We can only say the probability of finding that particular wave in a particular point. So, uncertainty principle could not match with Bohr's theory due to the wave nature of electron. So, this introduction of wave nature of electrons gives rise to one of the most important atomic model, that is known as quantum mechanical model. So let's start with quantum mechanical model. Now this quantum mechanical model, as I mentioned you earlier, considers wave nature as well as the particle nature of electrons. Now when we consider these electrons behaving as if like a wave, so the question of fixed circular orbit does not arise. So instead of this fixed circular orbit as were defined by Bohr's theory, we will define the probability of finding electron in a certain region of space inside an atom, and will replace this orbit by a term known as orbital. So orbit of Bohr's theory is changed to orbital. So circular orbit that was used by Bohr's theory, where electron revolves around this nucleus in a fixed circular orbit. Now that orbit, when we define the orbit, the exact trajectory, that is the position and the location, position and the momentum of electron can be precisely measured accurately simultaneously. But according to uncertainty principle given by Will Heisenberg, the exact trajectory of electron cannot be defined. That is, the momentum and the position of electron cannot be defined accurately simultaneously at any given instant. So, so that means this well-defined circular orbit is changed to another term that is known as orbital. So this orbital defines as the region of space inside an atom where probability of finding electron is maximum. Orbital is at a particular region of state inside an atom where the probability of finding electron is maximum. So we can talk of the probability of finding electron. So we have to define this, what is the probability of finding electron. Now since this considers wave nature of electrons, so this wave nature of electron is to be defined by a function which is known as wave function, similar to standing wave that we have used in physics. So wave nature is defined by a term known as wave function. Wave function pronounced as psi. So this wave function psi, this psi represents amplitude of wave. Now this will be something like standing wave. So this wave function psi means, to define this wave, we need to have a certain mathematical equation. That mathematical equation that defines a particular wave which represents electron is known as wave function psi, and this wave function psi of an electron represents the amplitude of wave. That means the displacement of the wave from the mean position, means the distance from mean to the maximum point, that is crest, or the minimum point, that is the trough. Now this wave function psi, which represents the electron, that is in quantum mechanical model, this is given by an equation. That means equation known as Schrodinger wave equation. So this was the scientist who proposed the wave equation similar to that of standing wave. That means the properties of this electron behaving as a wave, as if like a wave, can be expressed by a mathematical equation which can be used to define a standing wave. So similar to standing wave, we can define these electrons as a mathematical equation. That mathematical equation is given by a particular scientist which is known as Schrodinger, and the equation is known as Schrodinger wave equation. So this Schrodinger wave equation is the three-dimensional representation of wave. Three-dimensional wave equation. So coming to this Schrodinger wave equation, of electron, we have this del square psi del x square plus del square psi del y square del square psi z square plus 8 pi square m by h square e minus b psi equals to 0. So this is the three-dimensional wave equation which represents the electron in an atom. So we have looked at this, as I have mentioned, this psi represents amplitude of wave. This x, y, z, this represents Cartesian coordinates. because we are representing a three-dimensional wave, so wave will have its extension on x, y, and z, three dimensions. We have to take into account its extension in x-axis, y-axis, as well as z-axis. This del by square by del x square, y square, or z square, this represents second degree partial differential. This m represents mass of electron. H, Planck's constant. E, total energy of electron. V, potential energy of electron. So we have this equation which represents electron. This is known as Schrodinger wave equation. Now we have to modify this equation. So this wave function psi, which represents the amplitude of wave, depends on x, y, and z. Now these wave function psi can have, because this represents amplitude, so amplitude can be positive as well as negative, so this can have negative value or this can have positive value. So two values are possible for this amplitude, that is wave function psi. That means in an atom we represent electron by a wave, so this wave will have extension in positive direction or as well as negative direction. So that means the amplitude of the wave will have two possible values. Now, but the problem arises, we have to find the probability of finding electron. In an atom, inside this atom, we have to find the probability of finding electrons. The probability of finding electrons can never be negative. We can simply say the probability is there or there is no probability. Either the probability is 1 or the probability is 0. So there is no significance of negative value. So to overcome this negative value of wave function psi, this wave function psi is changed to psi square. Psi square. To psi square, this represents the probability. So this will always have positive. Positive always. So to overcome the negative value of this wave function psi, since the probability of finding electron cannot be negative, so we convert this psi into psi square. So in most of the case, we'll be using this psi square, which represents the probability of finding electron in an atom. So these probabilities, which represents psi square, will always be positive. So either the probability is 0 or we'll have a positive value. So we have this equation can also be written as delta square psi plus 8 pi square m by h square t minus psi equals to 0, where this delta square is equals to d square dx square del square dy square plus del square by dz square. That is known as Laplacian operator. So this is the main equation, or this can also be written in this particular form. Now the same equation can also be modified in this way, or this equation can also be written as h cap psi is equals to E psi. This is the shortest form of this Schrodinger wave equation. What is h cap is known as minus h square by a pi square m delta square plus v, and this is known as Hamiltonian operator, and this is nothing but total energy operator. So this total energy operator is nothing but kinetic energy operator plus potential energy operator. So the shortest, this long equation can also be written in the shortest form. That is h k. K represents a vector quantity. So we have the vector quantity, that is operator known as Hamiltonian operator, which is nothing but total energy, but that is kinetic energy plus potential energy. So we can this rearrange to give you this equation. Everything remains the same except this is the rearrangement. In terms of this E psi and this H psi, where H psi is this form. So we can also write this long equation into this shorter format. Now look at this. This wave function psi. Here we have this wave function psi. As I have told you, instead of this wave function psi, we will be using this psi square, which represents probability. Why? Because wave function psi have two possible values, negative as well as positive, but the probability of finding electrons cannot be negative. So to make this positive, we'll use this psi square, which is always a positive term. Now, if you look at this equation, x cap psi is equals to E psi, which represents this three-dimensional wave equation. This wave function psi has got some important properties. Only those properties, if the wave function psi satisfies only those properties, then that will be act as a wave function for electron. So let's see the properties of this wave function psi. Properties of this wave function psi. First thing, now this wave function psi is representing an electron wave. This electron wave should have a finite value. So psi should be finite. We cannot have infinite values of this wave function psi. This should be always a finite value. Number two, this wave function psi should be single valued. Only one value of this wave function psi is acceptable for a particular electron in any particular space in atom. So for one electron, we should have one finite value. So one electron can have two possible values of wave function psi. So for any acceptable values of wave function psi, these wave function psi should be well finite value as well as single value. Now this equation is in form of differential equation. If this is in the form of differential equation, the wave function psi should be differentiable. If this wave function psi is not differentiable, then at each and every point this comes out to be 0, so this is not possible. So this wave function psi should be differentiable. These wave function psi should also be continuous with number 5. These wave function psi should be an eigenfunction eigenfunction. So in mathematics, we have a function which is known as eigenfunction. So let me explain this eigenfunction. An eigenfunction is a function which, on operated by an operator, gives back the same function. So I repeat the definition. An eigenfunction is a function which, on operated by an operator, gives back the same function. Example of it is, so h cap is an operator operating on this wave function psi gives the same wave function. So these type of function which, on operation by an operator, gives back the same wave function multiplied by a constant, and this constant is known as eigenfunction or eigenvalue. So these wave function psi should be eigenfunction, and these eigenfunctions should always be associated with a constant which is known as eigenvalue. So wave function psi should be eigenfunction, and E should be the constant. That constant is known as eigenvalue. So these properties of wave function is acceptable. If these properties is not acceptable, then the electron is not possible here. For every electron in an atom, the wave function psi represents a particular value, and that value should be having these properties. Now coming back to this equation, as I have told you, psi should be an eigenfunction. Now look at this. This wave function psi doesn't have any importance in chemistry. This is coming into importance only when this is being operated by an operator. Unless this operator operates on this wave function psi, this wave function psi doesn't have any significance. So only when this wave function psi is operated by an operator, this gives you a quantity that is known as total energy of electron, and the same wave function is regenerated. Let me explain you in this in terms of a simple example. Suppose we have a brand new car. Now we have a brand new car. The car is completely, the fuel is completely filled up. We have a key. We have everything to run this car. Car is एकदम brand new. Key is with the operator. Fuel is completely filled up. Paper is ready. Everything is ready. The only thing is the car is to be operated by inserting the key. Without inserting the key, without igniting the car, that means unless the driver drives the car, what is the importance of car? If you keep on this car, the brand new car, after buying from the showroom, placing in the garage, it won't give any result, fruitful result. The importance of this car comes into picture only when this is being operated by the operator, that is known as driver. If the driver drives the car, then this gives you some product. So in the same way, this wave function represents the car, and this wave escape, the Hamiltonian operator, this represents the driver. So driver is operating the car. So when this driver operates the car, this some output is given after completion of this particular work. Again, the car remains as it is same. So this is something like this. So wave function psi comes into picture only when this is being operated by an operator. So without this operator, it has got its significance is less. So this comes into picture only when operated by this operator. Now, coming to the atoms, an atom is considered to be spherical in nature. Now, since atoms being spherical in nature, it's better to transform these Cartesian coordinates x, y, and z into polar or spherical coordinates. X, y, z, that is Cartesian coordinates. These Cartesian coordinates is changed to polar coordinates r, theta, and phi. This is known as polar or spherical coordinates. So, what is the requirement for this conversion of these Cartesian coordinates into polar coordinates r, theta, phi? The reason being, since atom being spherical, we consider atoms to be spherical in shape. So, to explain the spherical shape nature of these atoms, it is better to convert these Cartesian coordinates into polar coordinates having r, theta, and phi. These are represents the radial distance from nucleus, and this theta and phi represents angular dependence. So that means the initial wave function psi, which has dependence on x, y, and z, that is Cartesian coordinates. Now this is converted into polar coordinates. So these psi, x, y, z, wave function psi having dependence on x, y, z coordinates. Now this is transformed into psi, r, theta, and phi. So instead of this, we'll be using this psi, r, theta, phi to define an electron in an atom. Now these psi, r, theta, phi, that is total wave function r, theta, and phi. These total wave function, which depends on the coordinates r, theta, and phi, can be split into three different wave functions. So r function depending on values r. Then we have theta function depending on theta and phi. This is phi function. Theta depending on theta function. So these total wave function psi r depending on r, theta, phi is a combination of three wave functions. These wave function r, this is known as a radial wave function. Why this is known as radial wave function? Because it depends only on a radial distance from nucleus. Distance r from nucleus. So we have a wave function capital R, which depends on the value r, small r. So this is a radial wave function. Why this is known as radial wave function? Because the value of this radial wave function depends only on r and is independent of theta and phi. So r doesn't have any depends on theta and phi, angle theta and phi. R depends only on the radial distance from nucleus. So we said this is a radial wave function. This theta function and phi function, which depends on angle theta and phi, is known as angular wave function. angular wave function which depends only on angle theta and phi. Angle theta and phi. So this can be split into the product of the radial wave function and angular wave function. The radial wave function depends only on the radial distance r from nucleus and is independent of theta, phi and phi, angle theta and phi. And this part is known as angular wave function because this depends only on angle theta and phi. So this is angular wave function, this is radial wave function. Now, the complete picture of electron in an atom is defined by this total wave function, which is a combination of three wave function, r function, theta function, and the phi function. So, on solving this, we get different possible values of electron, which is acceptable for a particular given electron. This radial wave function depends on quantum number n and L. We'll discuss what is quantum numbers later on. But just for information, this radial wave function depends on quantum numbers n and L, whereas this angular wave function depends on quantum number L and M. These are quantum numbers. So we have this electron wave function. Cartesian coordinates converted into rectangular, spherical or polar coordinates. So total wave function is split into three different wave functions: r function, theta function, and phi function. R function is known as radial wave function because it depends only on distance from nucleus. Angular wave function is dependent only on angle theta and phi and is independent of r radius. This wave function, angular wave function, depends on two quantum numbers, that is L and M. The radial wave function depends on two quantum numbers L and L. So now let me give you some graph which represent this the radial wave function graphs. So I'll have to draw this part. A radial wave function. Suppose this is the radial wave function, or simply say this is psi, which represents radial wave function versus distance. So this is r function versus small r versus small r. This is called 1s orbital. We will define or this 1s 2s later on. 1s orbital. This is called 2s orbital. This is called 2p orbital. So this graph simply represents wave function r versus distance. So if you look at this graph, the wave function r is having maximum value at nucleus. This is nucleus, this is distance from nucleus. As the distance from nucleus, the wave function r decreases. The electron wave function is having maximum value at nucleus. Now the question is, if electron can be found in the nucleus, will the atom be stable? No. So the possibility of finding electron inside the nucleus is at 0. But if you look at this graph, radial wave function graph versus distance, the probability or the electron wave function is having maximum value in the nucleus. As the distance increases, wave functions are decreases. Same is the case in case of 2s. The only difference is again at nucleus, the wave function r is having maximum value. After a certain distance, this is having zero value, then again it becomes negative. So again, the probability of finding electron cannot be negative in an atom. But for this 2p graph, this seems to be okay. The radial wave function is having a zero value at nucleus, then increases, reaches a maximum value. After it is decreases. So somewhere in this point, there is a probability of finding electron. Now to overcome this negative value, as we have mentioned earlier, the wave function psi is to be converted into psi square, which represents the density. So we psi square or r square versus r. Now, if the values are square, the graph will remain as it is. On squaring this graph, the values will be square. The rest of graph will remain as it is. So there is no change. This is for 1s, 2s. This graph will remain as it is, but this negative will become the positive value. This will remain as it is. Only difference is graph will become much bigger. So again the same problem here. This represents r square represents probability density. So this is probability density versus distance from nucleus. Again the same problem arises here. Probability is maximum at nucleus. Again then decreases. For this 2s again, probability is maximum at nucleus, decreases. At this particular point, we have a probability finding of electron is 0. This particular point, where the probability of finding electron is 0, is known as node. This is node. Node is the region where probability of finding electron is 0. Any particular point in an atom where the probability of finding electron is 0 is known as node. Now, finally, instead of this probability density, we will define this in terms of probability. This is probability density. We will define this change into probability. So we have 4 pi r square into r. Then 4 pi r square into r. This distance is Bohr's radius 2s. So when we change this probability density to probability function 4 pi r square probability function, it gives the correct picture. So for this 1s orbital, the probability of finding electron is maximum at this particular distance, that is equivalent to Bohr's radius. At this point, the probability of finding electron is 0. We have a nodal point. For 2s orbital, there is a small probability of finding electron at this particular point. And then the maximum probability is at this particular point. So this is node, this is maximum value, maximum, minimum value. There is small chances of finding electron at this particular point, but the maximum chances is at this particular point. So these 4 pi r square, this is, so look at this is the probability of finding an electron in a small shell. Suppose look at this, we have this. Now this total volume, inside this total volume we take a small cell. Take this small cell. This distance is larger than this distance is r, this is r prime. So dr is r prime minus r. So the probability of finding electron in this small cell is known as 4 pi square. So don't need to derive all this equation. This is just to show you the probability of finding electron in very small cells will be defined. And once we define this probability of finding electron in very, very small shells, we can easily construct what is the overall picture of finding electron in a particular volume. So this is the significance of wave function, radial wave function graph. So simply saying the wave function r doesn't have any significance. This is the wave function square, which represents the probability that is showing the importance. So this represents the graph of the wave function r. So we have used a term known as node. So let's define this node. Node is a particular point over the plane where the probability of finding electron is 0. There's a place where probability of finding electron is 0. So any particular plane or a point where the probability of finding electron is 0 is known as nodal plane or nodal point. So inside this atom, there are many areas where this electron is not possible to find. Only those possible areas are known as orbital, where the chances for finding electron is maximum, and those particular areas where the probability of finding electron is 0 or electron is 0, that is known as nodal point or nodal plane. Now, while solving this wave equation r, theta and phi equation, that is the wave function which represents electrons in an atom, some important results comes out, and that important results are known as quantum numbers. These are the quantum numbers which are derived from the wave mechanical model. On solving this wave function r, theta, phi gives rise to 3 important quantum numbers. Now, before moving into these quantum numbers, let me explain what is quantum number. Now, we have to locate an electron in an atom. Now, to locate this electron, we need to have some specified variables. So, Once we know that particular variables, we can actually pinpoint what is there at this particular point, what is the nature of electron at this particular point. Like suppose we have to find a particular person X. A particular person X, we have to find this particular person X. You simply say, okay, find this particular person X. Will be able to possible to find? No. To find this particular person X, we need to know his country, in which country this particular person is X. So first requirement is we have to know the country. In this world there are so many countries, so there will be so many persons with this name X. So we have to pinpoint in which country this particular X belongs. So first we require X. Country. Once we know the country in which this particular person X belongs, next step inquiry is in which state of that particular country this particular X belongs. So our region for searching this particular X narrows down. Once we know this state in which this particular person X belongs, we need to know in which particular district this particular X belongs. So once we know the district in which this particular X belongs, again we narrow down this search area. And finally, what you have to know in which particular village, in which particular area this particular X belongs. So minimum we need to have 4 variables to define this particular person X. In the same way, to locate or to define an electron in an atom, we require minimum 4 values. The minimum 4 values which is required to locate or identify an electron in an atom is what we call as quantum numbers. These are values, means minimum values required to identify or locate an electron in an atom. So the 4 variables required to locate an electron in an atom is known as quantum numbers. So there are 4 quantum numbers. One is known as principal quantum number n, represented by small n. Second one is azimuthal quantum number small l. Magnetic quantum number small m, and spin quantum number. So we have these 4 quantum numbers. These 4 values are required to identify electron in an atom. So out of these 4, the first 3, principal quantum number, azimuthal quantum number, and magnetic quantum number, these 3 are derived from wave mechanical model. That is, on solving the wave equation, the wave function psi, on solving this wave function psi, this gives rise to 3 quantum number, that is n, l, n. I have given you. The radial wave function depends on n and l, that is principal quantum number and azimuthal quantum number, whereas the angular wave function depends on azimuthal quantum number and magnetic quantum number. Later on, this spin quantum number was used to identify the spin of electron, because electrons was found to spin either in positive direction or in negative direction. To account for this, the 4th quantum number, that is spin quantum number, was introduced. So this 4 quantum number is required to define an electron, to pinpoint a particular electron in an atom. So this is what we call as quantum number. So we'll take up one by one. First we'll take up principal quantum number. Now this principal quantum number is represented by symbol n. So this was the same n that we have used in Bohr's atomic theory. Because one of the very important postulates of Bohr's theory says the angular momentum of electron should be some integral multiple of h by 2 pi. So that integral multiple was n, which represents the shell number. So this n represents shell number. So when this n represents shell number, the values of n cannot be 0, but n can have 1, 2, 3, 4, etc. N cannot have negative value, n cannot have fractional value, n cannot have 0 value, and only possible is 1, 2, 3, 4, 5. If n equals to 1, we say this is K shell. If n equals to 2, we say this is L shell, P, M, N, O, etc. So this simply represents the shell number. This n also represents the angular momentum of electron, that is mvr is equals to n by h pi, that is from Bohr's theory. This cell number also gives rise to energy. Defines the energy of electron. We say En is equals to some minimum value z square by n square. So this n represents the shell number. So once we know the shell number, we can easily define the energy of electron in that particular shell. This also represents the radius. Obviously, we see the shell number 7 is the size of. So we have Rn is R naught n square by z. Again, look at this. This n represents the size of the shell. So this is principal quantum number. So first thing we require is to define this electron. We have to say in which shell that electron belongs. Once we know the shell, either we can have K shell, L shell, M shell. So once we know the shell, we can define the angular momentum, we can define the energy, we can also define the radius. Now this value of n also defines the number of orbitals, the total number of orbitals possible in any given shell. This is given as n square. So n square represents the orbital. This also gives you total number of electrons possible in any given shell, that is 2n square. So once the value of n is known, we can easily define how many orbitals. I suppose we have defined the orbital, the property of finding electrons. So how many orbitals are possible in any given shell, that is given by n square. And the total number of electrons possible in any given shell is given by n square. So therefore look at this. First shell, that is K shell, n equals to 1. So this is cell. Orbital, electron. So K shell, n equals to 1, 1 square, 1. So we have 1 orbital, total electron, 2 electron is possible. This is n. L shell, value of n is 2, so total orbital is 4, total electron is 8. Third shell, total number of orbital is 9, total electron is 18 is possible. 4, n, total number of orbital is 16, total number of electrons possible is 32, etc. So once we know the value of n, we can define how many orbitals are possible in that particular shell. And once we know the number of orbitals, we can easily predict what are the possible values of electron, how many electrons can be fit in that particular shell. So this is the force that gives you the principal quantum number. Second quantum number is azimuthal quantum number. This is also known as orbital angular momentum quantum number. This is also known as subsidiary quantum number. So this is second. Azimuthal quantum number, orbital angular momentum quantum number, and subsidiary quantum number. Means the same thing. This is given by value L. So L, small l, represents the azimuthal quantum number. Now this L represents subshell. That means we have this cell. Inside this cell we have some smaller subcells. So first we define shell, and inside this cell there are some small shell. That subshell in a cell is represented by this azimuthal quantum number. So with this L defines subshell. This L also defines the shape of orbital. Shapes of orbital will give you the shape electron. The values of L 0 to n minus 1. That means the value of L is defined provided we have the value of n. Without defining the value of n, we cannot have L. So if you look at this, L can be 0, but L cannot be equal to n. The value of L is always less than n. So any orbital in which the value of L and n is equal, that is not possible. The value of L should always be less than n. And L can be 0, but L cannot be negative. L is only positive value, including 0. So if the value of L is 0, we say this is S subcell. If the value of L is 1, we say this is P subshell. As the value of L is 2, we say this is D subshell. As the value of L is 3, we say this is F subshell. If the value of L is 4, we say this is G subshell, etc. Now this term S represents sharp, P for principal, D for diffuse, F for fundamental, G for generalized. These are not spectroscopic words. So look at this. For the value of L, the subshell is fixed. L equals to 0 S subshell, 1 P subshell, 2 D subshell, 3 F subshell, 4 G subshell. Now this is subshell. This is subshell. Name of subshell. S subshell, that is spherical. Spherical. S is always spherical. P, that is dumbbell shape. D, this is double dumbbell. This is the shape of orbital. Now since this F and G, this is much more complicated, so we are not discussing this F and G. We are focusing on this SPE. So S is spherical, P is dumbbell shape, D is double dumbbell shape. So this L represents the subshell, also represents the shape of orbital. So L can have these values. And this L also represents, once we know the value of L, we can also define the total number of, so we have this L, azimuthal quantum number, orbital angular momentum, subshell, shape of orbital, values, possible values, and for this L, subshell is fixed, and what is the shape of subshell. So once we have this value of L, we can define number of orbitals in any given subshell. So total number of subshells possible in any given of, total number of orbitals in any given subshell is given by twice L plus 1. So look at this S subshell. Number of orbital is twice L0 plus 1. So S subshell has got one orbital. P subshell 2 into 1 L is equals to 1. So plus 1, that is, so D subshell has got 3 orbitals. D subshell number of orbital is 2 into 2 plus 1. So D has got 5 orbitals. Similarly, F 2 into 3 plus 1, 7. G 2 into 4 plus 1. So once we know the value of L, we can define how many orbitals are possible in that particular subshell. So the number of orbitals in any given subshell is given by this will, that is twice L plus 1. And this L also gives total electrons possible in a subshell. So in any given subshell, how many total electrons are possible? So this is twice L plus 1. So therefore look at this. S, how many orbital? 1. So how many electrons is possible? 2 electrons. 2 electron is possible. E, how many orbitals? 3. So 3 into 2, 6. 6 electron is possible in P subshell. D, how many subshell? 5. 5 into 2, 10 electron. F, how many subshell? Subshell is F. How many orbitals? 7. How many electrons? 14, etc. So this angular momentum quantum number gives number of orbitals. And once we define the total number of orbitals possible in this subshell, we can also define how many electrons are possible in that particular subshell. That is azimuthal quantum number, which defines the subshell in any given shell. So we have shell, inside this we have subshell. After this, the third quantum number is magnetic quantum number. Now we have a shell. Inside this we have subshell. Now this splitting of shell into smaller subshell, that is what we call as Stark effect. That one of the more important effects of Bohr theory was splitting of single lines into number of lines when this is placed in electric field. So when this line is placed in electric field, this line is split into number of smaller lines. That is Stark effect. So this second quantum number, azimuthal quantum number, gives rise to the splitting of this single line into smaller lines. Magnetic quantum number, small m, this represents magnetic quantum number. This magnetic quantum number defines subshell. That means we have a shell. Inside this we have subshell. Inside this subshell we again have subshell. So that subshell is what we call as orbital. So the subshell in a subshell is defined as orbital. This is the place where the probability of finding electron is maximum. So this M represents the orbital or subshell. These M can have values of M is minus L passing through 0 to plus L. That means the maximum value of L is equals to L. Maximum value of L is equals to L. So the value of M and L can have same. The maximum value of magnetic quantum number M is equals to a symmetric quantum number L. Now this M can have 0, M also can have L. So total values of M, total possible values of M is twice L plus 1. That represents the orbital. So the value of L defines the value of M, and the total possible values of M is twice L plus 1, which is nothing but the total number of orbitals that we have defined in the previous quantum number. So look at this. If L equals to 0, M equals to 0. So we have one value, L into L plus 1, 0 into 2 plus 1, only one value, one value. If L equals to 1, M can have 1 into 2 plus 1, 3 values. So we have plus 1, we can have 0, we can have minus 1. So when L equals to 1, this is S, this is P subshell. So P subshell has got how many orbitals? 3 orbitals. S subshell has got how many orbitals? 1 orbital, that is S orbital. So this P has got 3 orbitals. Orientation is plus 1, orientation is minus 1, 0. This plus minus 1 and 0. 0 is Pz, whose orientation is along Z, plus minus 1 is Px or Py. That is convention. Z axis is, so we have one orbital pointed around Z axis, one along X, one along Y. So look at this. This is suppose Y, this is X, this is Z. So we have this. So in this, look at this, orientation is purely along X. So we say this is Px. That is Y, X, Z. This is Py. This is X, Y, Z. So the lobe of this dumbbell can have its orientation along x-axis, y-axis and z-axis. So based on this, we have 3 possible orientation of this P subshell. That is 3 orbitals. Px orbital, whose orientation is purely along x, y purely along y-axis, z purely along z-axis. So we have these 3. D subcell, the possible value of L is 2. So M can have 5 values: -2, -1, 0, +1, +2. There are 5 possible values of D. That means there are 5 possible values of D. That means there are 5 possible D orbitals. So we have this. So this D has got 5 orbitals: D xy, D yz, D zx, D x square y square, and D z square. These two are known as axial orbitals because they have orientation around axis. These three are known as non-axial orbitals. These non-axial orbitals have orientation in between the axes. So these 5 is classified into 2: non-axial orbital, in which the orientation is in between the axis; axial orientation along the axis. So let me draw the steps of these 5 orbitals. dxy, orientation is in xy plane. So we have this. Suppose this is y, this is x. So this dxy is in between x and y axis. This orientation is actually 45 degree to x as well as y. So this is xy plane, xy plane, xy plane, xy plane. This doesn't have orientation along axis. So we have to look at this. This particular plane, this plane, probability of finding electron, this is a node, and look at it, this plane. Again, this plane, that is node. We have two nodal planes here. D, Y, J in YJ plane. Suppose this is Y, this is J. So we have in between Y and Z axis. Again, look at this plane. This is nodal plane, this is also nodal plane. So in XY, XZ, we have nodal plane. Then we have D, ZX in ZX plane. Suppose this is Z, this is X. So we have this. Then we have dz square along z-axis. Its orientation is purely along z-axis. So we have looked at it. That is dz. So we have this z-axis. Now with this is also have some chances here. This is z-axis, and finally we have dx square y square along x and y axis. So suppose this is y, this is x. So this purely along x and y. That is y-axis. This. So these are the shapes of this 5D orbital. So purely along x and y, purely along z. That is in zx plane or in between z and x. YZ plane or between y and z axis. XY plane or in between x and y. So this magnetic quantum number defines the orientation of the orbitals in space. In which particular direction this orbital has got this orientation. So this orientation is along x and y. Orientation is along z axis. This is xz plane, xy plane, yz plane. So this is magnetic quantum number which defines the subshell or subshell. Then the fourth quantum number is spin quantum number. Now, it was found that electron also spins like a top. So, this is given by spin quantum number S, and this spin quantum number S has got only two possible values. Either we can have positive spin or we can have negative. So, only two possibilities, plus half or minus half. So, plus half is known as this. This is also known as clockwise spin. This is anti-clockwise. So, spin quantum number represents how this electron spins when this is moving around this nucleus on spin. So, look at this. These are the four quantum numbers which exactly defines an electron in an atom. So, to define this electron, we require these four quantum numbers, and these four quantum number only foresee N, L, M is derived from quantum mechanical model. The rest spin quantum number is not defined from the wave mechanical model. So this is the wave mechanical model, and from which we derive these four quantities. Now once we have these four quantum numbers, we'll define the electronic configuration. So for today we'll conclude here. Thank you.